This is T3, trimester 3, day 2. I'll try and make this a little shorter than yesterday's video. This is integrals continued. So we're starting off with the same example we finished with yesterday, and that is this table of values that represents time as your x value and velocity as your y value, time in seconds, velocity in feet per second. So it's the same table of values we had yesterday and the same graph that we had yesterday. What I'd like to look at again today, and we did look at this yesterday, so I'll go through this pretty quickly. If you're still confused by it, you may want to go back and look at the day 1 video again. So what we've done is we've taken these gray rectangles representing the underestimate. So for the entire first 1 second interval, we're assuming that the car traveled at a velocity of 20 feet per second. For the second 1 second interval, we're saying we're going to assume the least possible velocity, and that's the 30 feet per second. And for the third interval, we're going to assume the least possible velocity at 38 feet per second, etc. That's the underestimate. We can also look at the entire rectangle that goes up to the top and a height of 30 and say that in the first interval, we're going to assume that the car got off the mark pretty quickly and didn't stay at 20 feet per second for long at all, but for the entire interval, we're going to assume that it went the fastest speed possible, so the 30 feet per second. During the second interval, again, we're going to assume the fastest, the 38 feet per second for the entire interval. So we have the underestimate, which is shown here in gray, and the overestimate, which is the gray plus the red. The difference in distance, remember distance is expressed as the area underneath the curve or the area within the rectangles, because we're looking at feet per second times second, which would give us feet. So the area under the curve or the area of the rectangle is representing the distance we traveled. So the difference between the overestimate and the underestimate is this area that's shown in red for each one of the 1 second intervals. If I take each of these little rectangles, slide them over and stack them up to make one stacked difference rectangle. So I'm going to take this rectangle, put it over, stack it, stack it, stack it. This red rectangle represents the disputed area, the disputed distance. So in this case, if I want the area of this rectangle, the height is the total height of 48 is the highest value. The lowest value is 20. The difference there, 48 minus 20, gives me 28, times this delta t, the width of the rectangle in each one of these increments, is 1 second. So I've got 28 feet per second times 1 second gives me 28 feet. So that's the error rectangle. And it's always the difference between the initial value, initial y value, and the ending y value in a monotonic graph. Monotonic graph sounds like it's something confusing. It actually means it's just either always increasing or always decreasing. So it's not going up for a little while, down for a little while, up for a little while, down for a little while. It's like a sine curve would not be monotonic. But this is continuing to go up. So it's monotonic. If it continued to go down, it would be monotonic, descending. Okay, so the difference between the lower and the upper estimates is that f at b minus our f at a times our delta t. And again, we're calling this our a value. This is our b value. These are our x's, these are our y's. So this is the f at a, our y value at a. This is our f at b, our y value at b. How frequently must the velocity be recorded in order for the lower and upper estimates to be within 5 feet of each other? So right now our lower and our upper estimates were within 28 feet of each other. Well, I want a better I want a better measure than that. I want them to be closer. So we'd need to send our team out to measure more frequently, get these closer together. Remember yesterday we also looked at measurements that were each increment, each delta t was 0.5. Well, in order to get the difference to be 5 feet, what would we need to do? Well, I'm going to come back to this and say, well, if I've got my f at b minus f at a times my delta t gave me 28, I'm going to need to change my delta t. So what would that delta t need to be? Well, I'm going to take my f at b minus f at a, multiply it by some delta t that I'm going to try and find, and I want that to give me a value of 5. Well, my f at b is 48, my f at a is 20. I'm multiplying that by delta t to give me 5. So delta t must equal 5 over this 28, or approximately 0.179 seconds. So the increment, the width of the increment, how often, is the 0.179. Now also I could ask, well, how many intervals are there? If I want to know the number of intervals, remember from yesterday that we said the number of intervals is equal to b minus a over delta t. So the n is equal to my b value, 4, minus my a value, 0. 4 minus 0 over this delta t that I just found, 5 over 28. I'm going to go back to the exact value. So n equals 4 times 28 over 5. So my 4 times 28 gives me 4 times 28 is 112 divided by 5 gives me 22.4 intervals. Well, I can't have a 0.4 intervals. If I either have the interval or I don't. So I want n to be a whole number. And if I want to have to be within 5 feet, I've got to have at least 22.4 intervals. So if I were to round this down to 22, I'm not going to come as close as that 5. So I'm going to need to let my n equal 23 intervals. So this part wasn't asked for in the problem, but it certainly is something to consider and to look at. So as this problem was asked, it's how frequently we must take a measure every 0.179 seconds. Okay, so now in general, this error we talked about yesterday, we take the difference of the upper and lower, multiply it by our delta t. We're going to toss that in absolute values. And the reason is, if I had a descending function, where my f at b is lower than my f at a, well, if I had an f at b minus f at a of a 3 minus 20, I get a negative 17. Just doesn't make sense to then say, well, what is my error? It's going to come out to be a negative number. So if that value, the f at b minus f at a, turns out to be a negative number, just take the absolute value and so you're making it positive and multiply by your delta t. This is a really important equation for us to have. You're going to want to come back to that, and we're going to be using that often. So make sure you've got that highlighted. Okay, so another thing that just it's not a hard distinction, but something we want to be aware of is that we sometimes call this gray area the underestimate. Sometimes we call it the lower estimate. We can also call it a left-hand sum. Now, left-hand sum, this sounds like it's something that's so tragically hard, but what we're really going to do is say that, well, in our rectangle, on this curve, it's the upper left corner that hits the curve. So these gray rectangles become a left-hand sum. If we look at the combined gray and red rectangle, it's the upper right-hand corner that's hitting the curve. So we call that a right-hand sum. Just another way of referring to the underestimate or the overestimate. So in this case, with this increasing function, the left-hand sum is an underestimate because it doesn't give us the full area under the curve. It gives us a little bit less. It's a reasonable estimate, but we do leave out these portions. So it's a lower estimate than the actual value, which would be the full area under the curve. The right-hand sum gives us this extra space that's not actually under the curve, so it's an overestimate. If we come back and look at this really rough sketch, if I draw in these rectangles that are underneath the curve, it's an underestimate of the area. It's the upper right-hand corner that's now hitting the curve. So in this case, it's a right-hand sum, and it is an underestimate. So we can't say that the left is always an underestimate or the right is always an underestimate. It depends on whether the curve is an increasing or decreasing function. For that left-hand, right-hand sum, we can also look at our table of values. And in the whatever interval we're looking at, if we're going to take the value that's on the left and add them up, so for my left-hand sum, I would have 20 times 1 plus 30 times 1 plus 38 times 1 plus 44 times 1 using the left value in each interval. That's a left-hand sum. So we're going to refer to these sums as either underestimates, overestimates, lower estimates, upper estimates, left-hand sums, right-hand sums, all having the same process. It's just a different way of expressing what we're looking for. So those are really the only notes for today. We also went on to do this oil leak problem, and we did this in partners in class, but I'll go through it here, so if you weren't in class, you can still see what we did with it. Suppose oil is leaking out of a container at a decreasing rate. This rate is measured in hourly intervals given in the table below. So time in hours and the rate in liters per hour. So we've got over a 4-hour period, and the liters per hour initially leaking out at 35 liters per hour and eventually at 21 liters per hour. So find an underestimate for the total amount of oil that is leaked out of the container over the 4-hour time period or 4-hour interval. So if I want an underestimate in this first interval, I'm going to take the 30. In the second interval, the lower value is 26. In the third interval, the lower amount is 23. And in the fourth interval, the lower value is 21. I need to multiply that by the width of each interval, which is 1. So I have that equals 100 liters. My overestimate, I will do similarly. In this interval, I'm going to take the 35. In the second interval, I'll take the 30. In the third interval, I'll take the 26. And in the fourth interval, the 23, multiplied by the width of the interval, which is 1, and I get 114 liters. Now, just a quick aside, looking at not only the underestimate, overestimate, but left-hand sum, right-hand sum, if I'm looking at this interval and I take this number, which I did here, because that's the number that's on the left, this is a left-hand sum. So while this is an overestimate, it is also a left-hand sum. In this interval, when I take the number that's on the right, it is a right-hand sum. So my problem didn't ask me for that, but I just wanted to reinforce left-hand sum, right-hand sum. If you had to guess how much oil actually leaked out in a 4-hour interval, what would be your guess? Well, technically, the best we can do is to say that the actual value, actual amount, must be something greater than 100 liters and less than 114 liters. If I was really pressed for a best guess, I would average those two, and I'd say 100 plus 114 over 2 would be 107 liters. This is your most accurate way of expressing what do we know about the oil that's leaked. It's somewhere between 100 and 114 liters. And what is the maximum possible error in your guess? In other words, what is the maximum possible difference between your guess and the true value? Well, if we had guessed 100 liters, and we know it could have been all the way up to 114 liters, well, then the most error I have, as long as I guessed a number somewhere in this range, the furthest off I could be is 14 liters. Intuitively, we get that answer. But we also want to go back to knowing that we can find our error, find our accuracy, with error equals the absolute value of f at b minus f at a times delta t. So our error is our f at b is 21, our f at a is 35. So 21 minus 35 times our delta t, and our delta t is 1. So we've got the absolute value of negative 14 times 1 equals 14 liters. And that's what we got intuitively. So the back page, we sent the team back out and we said, we want more measures than what you gave us the first time. Go out and measure every half an hour. So they did that, and recalculating the upper and lower estimates in light of this new information. For our lower estimate, we're going to take the lower value in each one of these intervals. So our lower is we have 33 plus 30 plus 27 plus 26 plus 24 plus 23 plus 22 plus 21. And we're going to multiply that by the size of the interval, which is 0.5. So we have 0.5 times 206, adding these values on a calculator, and we get 103 liters. For our upper estimate, we're going to take the larger number, in this case it's the left number, starting with the 35 plus 33 plus 30 plus 27 plus 26 plus 24 plus 23 plus 22. And just a little caution here, I often see people just get carried away. They're writing the numbers and they just take all of them. Remember that in that last increment, last interval, we still just want to take that largest number. So we're not taking the 21. And we're multiplying by the width of the interval, which is 0.5. And just a little bit of a calculator shortcut here. I could add all of these again in my calculator, certainly easy enough to do. But I could also say, well, okay, I've got this 206 that I know already. The 33 is not included in the 206. So on my calculator, I've got 206. I'm going to subtract the 33, but I'm going to add in the 22. And I now have 0.5 times 220. If you don't use that shortcut, it's no big deal, but sometimes it's just quicker on the keystrokes. So that would give us 110 liters. So make a new guess for the total amount of oil which was leaked out of the 4-hour interval. Find the maximum possible error of your guess. Okay, so I'm going to say that my actual amount has to be between 103 liters and 110 liters. If I needed to give a best guess, I would say, all right, so 103 plus 110, I'm just going to average these, and I get 106.5 liters. This is the most accurate way to express it, to say that the actual amount is between 103 and 110, but if somebody presses you for a best guess, we would say the 106. Well, the difference between my lowest and highest is this 7 liters, going from 103 to 110. But I can also express that as my error is equal to F at B minus F at A, absolute value, times delta T. My F at B is still 21. My F at A is still 35. But my delta T now is 0.5. So I've got absolute value of negative 14 times 0.5 is equal to 7 liters, which we intuitively got by going from 103 to 110. So the difference is 7 liters. If the readings of the rate were obtained every 10th of an hour, by how much would your upper estimate exceed your lower estimate? So that's asking how far apart would these two numbers be? If I measured every 10th of an hour, well, what does this every 10th of an hour represent? It represents our interval and how wide the interval is. So we're looking for the error. We're looking for how far apart would these measures be if F at B minus F at A is now, in absolute value, is now multiplied by a delta T that is 1/10. So my F at B minus F at A is still 21 minus 35 is going to be my error. So 14 times 1/10, which is 1.4 liters. And what if the readings were obtained every 100th of an hour? Well, it's the same problem, but now my error is equal to 21 minus 35 absolute value times 1 over 100. So it's equal to 14 over 100, or 0.14 liters. So this just becomes my delta T value. And then how often would you have to take your readings to get the difference between your upper and lower estimates to be just 1 liter? Okay, so I'm going out in front of I'm the spokesperson for this oil company that's got oil gushing out in this leak, and I need to be able to tell people within 1 liter how much oil is leaking out. So I've got to tell my engineers out on the platform how often I want them to take the readings so that they can give me this accuracy. Or perhaps the engineers out on the platform have to do this calculation to figure out how often they have to take the reading. So I'm looking again for error. I'm still going to be using my F at B minus F at A and my delta T times delta T. I want my error to be 1 liter. So my F at B is still that 21. My F at A is still the 35. This is the rate at the end. This is the rate at the beginning in absolute values. But I need to find my delta T. So 1 equals 14 delta T. Delta T equals 1 over 14 hours. If I needed to find how many measures would there be, I would use that N equals B minus A over delta T to find out how many intervals there are. But if I'm going to be instructing the engineers out on the platform, or the engineers out on the platform have to figure this out, how often do they need to take those measurements, they would have at that point right now know that it's every 1 over 14, and 1 divided by 14 is 0.07 hours. So every 7/100ths of an hour, they need to be taking a measurement so that they can get their error to be just 1 liter. So hope that helps, and see you tomorrow.